Okay, right. So we are now going to continue. We are still on module 1, heating and expansion of gases. Okay, and then just see if I can zoom in here. Okay, right. What we've done now, is we've essentially covered the learning outcomes. Okay, we've covered the learning outcomes. What do I mean when I say we've covered the learning outcomes? Module 1, heating and expansion of gases, learning outcomes. Now, when you have learning outcomes, essentially there's 5 things that you need to know with regards to learning outcomes. Now, 2 of the 5, it deals with describing. The other 3, it deals with calculating. Now, when you describe, you have to be able to describe laws of thermodynamics, okay? You also have to be able to describe gas processes, okay? And then the stuff that you should be able to calculate, they involve calculating. Okay, right, that should be better. It involves calculating the heat transferred on a gas as well as the work done on or to a gas. On or to, we've referred to this as qualifiers, okay? I'm not really sure what that word means, but it sounds right, okay? Right, work done on or to a gas, simply meaning it's 2 different things, okay? As well as calculating the internal energy of a gas, okay? Internal energy of a gas. Then also, what we did mention was that since temperature and air pressure, simply meaning temperature and air pressure, since temperature and air pressure vary, simply meaning they change. Initial temperature and final temperature is 2 different things. Initial air pressure, final air pressure is 2 different things, meaning they vary. Vary means change, okay? From place to place. Simply meaning if you are at A, B, C, or D, these are regions in space, it's going to be different. What is going to be different? Your temperature as well as your air pressure, okay? Right. It is necessary with a standard referencing condition, okay? Now, that is what we did over here. We said standard referencing condition, okay? Standard referencing condition. What does that mean? What that simply means is the following. Now we have to pay attention because now we are dissecting, okay? Right. Since temperature and air pressure vary from place to place, it is necessary with a standard reference condition to compare. Simply meaning the standard reference condition, it is there for 2 things. 1, it is there to compare, okay, testing and documentation. Simply meaning we are there to compare what 2 things. What are those 2 things? Testing as well as documentation of what? Of chemical and physical processes. Okay, so that is the introduction. Now, as a side note, when we are talking about thermodynamics, okay, thermodynamics, whatever that is, fancy word, big word, right? Thermodynamics, it is, okay, how should I put it? It is a description through which we are linking 3 things. So when we say thermodynamics, it's just a fancy way of describing the relationship between 3 things. That's it, okay? Obviously, there are some more scientifically sound, mathematically rigorous descriptions, but for now, we are trying to keep things basic, okay? Thermodynamics, big word. What does that word mean? That word, it basically speaks to the relationship between 3 things. What are those 3 things? Heat, that's the first thing, okay? Work, that's the second thing. And then properties of a gas. That's it. Heat, work, properties of a gas. The moment you talk about those 3 things, essentially you are talking about thermodynamics. Now, when we say properties of a gas, that can mean anything. Okay, so let's just define some of the properties of a gas. That's just so that we can be on the same page. Okay, right, here goes. Properties of a gas, they include the mass of a gas, as well as the specific heat and energy of that gas. That's it for now, okay? Right, so now we have been briefed, okay? So now let's continue. Okay, right. For us to continue with heating and expansion of gases, we need to note something, okay? What is it that we need to note? A thing that we need to note is at some point, we will have to do what we call measurements, okay? Measurements. If we talk about mass, it's something you should be able to do what? To measure. If you talk about length, something that you should be able to do what? Measure, okay? If we talk about temperature, it should be something that at some point you should be able to measure, okay? So the following terms are used for taking accurate measurements. Simply meaning when we refer to accurate measurements, there are some key terms associated with that. Okay. Right, what are some of these key terms? Okay, some of these key terms, we refer to them as absolute temperature. For now, I'll just say 1.1.1 absolute temperature. Okay, absolute temperature or thermodynamic temperature, absolute temperature or thermodynamic temperature. Okay, your absolute temperature, it is defined by the third law of thermodynamics. Simply meaning this thing called thermodynamics, it has three things associated with it. However, there are also some laws associated with thermodynamics. Okay, and then if we continue, we will find that theoretically speaking, the lowest temperature is the 0 point. At this point, absolute zero. We refer to it as absolute zero. What do we mean when we talk about absolute zero? Absolute zero, it simply means that the particle constituents of matter, it has minimal motion and can become no colder. Obviously, you have particles. These particles, they vibrate, meaning if you heat them up, the particles vibrate. They increase in terms of vibration, okay? But now, if we reduce heat, meaning we are extracting heat from a system, that is the process known as, making it colder, okay? If you continue with that process, it gets to a point where your particles, the movement of those particles, it's minimum, or what we call minimal movement, okay? And then at that point, we call that absolute zero. Okay, simply meaning you can no longer extract heat or excess heat from such a system. It, in simple terms, means it can no longer become any colder. Simply meaning you get cold, and then you get to a point where it cannot become colder. Okay, now absolute temperature, it is referred to, absolute temperature, it is referred to as, okay, right, let's do this. It is measured in Kelvin. Okay, absolute temperature, it is measured in Kelvin. It's a capital letter K. Okay, right, there we go. Now, when we refer to absolute temperature, essentially speaking, we are talking about 0 degrees Celsius. Okay, now if we say 0 degrees Celsius, this is actually what we are meaning. We are actually saying that 0 is 273 Kelvin. Okay, but let's go further. Because remember, now we are talking about absolute temperature, so we are now trying to wrap our head around the phenomenon of absolute temperature. Now, if we say 0 degrees Celsius, please note, that is still not really absolute temperature. Simply meaning, we have to find a way of working our way in the direction of absolute temperature. And then this is the starting point. We say 0 degrees Celsius, and then that will equate into 273 Kelvin, okay? Now, let's go further. If I'm up 273, how do I get to 0? It's simple. What do? I say minus 273. Then I get to 0. 0 what? 0 Kelvin. It's really that simple. Okay? However, what I do on the right, I also have to do on the left. So now I say minus 273. What does that bring me? If I'm at 0 and I subtract 273, essentially speaking, now I end up at minus 273 what? Degrees Celsius. Simply meaning 0 Kelvin is equal to minus 273 degrees Celsius, and that's minus 273 degrees Celsius, otherwise known as your 0 Kelvin. That is what we refer to as absolute temperature. Okay, right. Now let's continue. Okay, there is also what we refer to, what we refer to as the standard temperature and pressure. standard temperature and pressure. Okay, STP, standard temperature and pressure. Okay, right. STP, it is commonly used to define standard conditions for temperature and pressure, which is important for the measurement and documentation of chemical and physical processes. Now, when we talk about STP, we are talking about pressure. Okay, so for now, let's say pressure. Okay, let's also go when we say temperature. Now, when we say pressure, pressure equals to what? It's 101.325 kilopascal, and then the temperature, it is 0 degrees Celsius. Okay, so when we are referring to standard temperature and pressure, for pressure, it's 101.325 kilopascal. For temperature, it is basically 0 degrees Celsius. Now let's continue. Let's continue. Okay, there is also what we refer to as normal temperature and pressure. Normal temperature and pressure. Normal temperature and pressure. Okay, right. Normal temperature and pressure. It is commonly used as a standard condition for testing and documenting or documentation of fan capacities. Where now we will talk about pressure, and then we are going to talk about temperature. Okay, right, and then the temperature at this point, it's 20 degrees Celsius, and then the pressure, that's your NTP. Okay, right. Then there's also what we refer to as standard atmosphere. Okay, right. So standard atmosphere, I'll just say STD. STD refers to standard, and then ATM, standard atmosphere. Yeah, I'm not going to write out the full stuff, so yeah, standard atmosphere. Standard model of the atmosphere adopted by the International Civil Aviation Organization, okay, where pressure is equal to, and then also temperature is equal to 15 degrees Celsius, and then your pressure is 101.325 kilopascal. Okay, right. So yeah, so that is what's happening over there. And then also right, the thing that we also have now is something called heat and expansion of gases. Heat and expansion of gases. Okay, now thermal expansion, okay, it is the tendency of a gas to change in volume in response to a change in temperature. This is through heat transfer. Okay, so there's this phenomena, otherwise known as heat transfer. What is heat transfer? Heat transfer is basically where heat is transferred from body A to body B. Okay, heat transfer. Now, there's an association with heat transfer, otherwise known as thermal expansion. Thermal expansion, it is the tendency of a gas, simply meaning gas, it has an inclination, okay, to change in volume. And then this change in volume, it is in response to a change in temperature. Simply meaning if you vary the temperature of a gas, fundamentally speaking, you are also varying the volume of that gas. Okay, and this is playing out in a process called thermal expansion in relation to what is otherwise known as heat transfer. Okay, right. Now also temperature, it is a function of the average molecular kinetic energy of a gas. Simply meaning whenever we are talking about the temperature, whenever we are talking about the temperature of what? Temperature of a gas, okay? It is talking to something about the gas. If I say temperature of a gas, I'm actually speaking to an attribute, a characteristic of the gas. What is that characteristic? That characteristic, it is the average molecular kinetic energy. Simply meaning kinetic energy, average means what? Most of them, okay, have this thing in common. And then, now, this is what's key. Temperature, it is a function of the average molecular kinetic energy of... Now, when we say kinetic energy, simply meaning it refers to movement. That's it. Okay? So, temperature, it is a function of the average molecular kinetic energy of a gas. When a gas is heated, the kinetic energy of its molecules is increased. Thus, molecules begin moving more and usually maintain a greater average separation. Okay? The degree of expansion divided by the change in temperature is called the gas coefficient of thermal expansion, and generally varies with temperature. All of that is just a fancy way of saying the degree of expansion. Okay? Expansion is what? It speaks to volume. Okay? Meaning the change in volume divided by the change in temperature. It is called the gas coefficient. Simply meaning a gas coefficient, it is a unique way of describing a particular gas. Okay? Of thermal expansion and generally varies with temperature. That's it. Okay, so that is what we refer to as heat and expansion of gases. Then now let's go further. There's this other thing. Nah? It's called specific heat. Specific heat. Okay, specific heat. Let's just write that down. Specific heat. Now, when we are referring to specific heat, we need to describe the thing it is that we are talking about. The best way to describe the thing it is that we are talking about is the following. The amount of heat transferred. Now, when we say heat transferred, essentially we are talking about energy required. So if you are transferring heat, essentially speaking, for that to happen, there's energy, which is a minimum requirement in order for this heat to be transferred. So specific heat is what? The amount of heat transferred, meaning the minimum energy required to raise a unit of... Okay, look at it like this. Let me draw a picture. Here's a picture, all right? This is a picture of what? Of gas. This gas, it has a mass. Okay? For now, let's refer to this mass as unit mass. Okay? Now, if you want to, or let me write it out as mass. Okay? If you want to increase the temperature of this unit mass of a gas by 1 degree, for now let's say Celsius. I don't want to commit myself to 1 degree Celsius, but if I say 1 degree Celsius, it will make sense to you. If I want to increase the gas of a unit of mass by 1 degree Celsius in temperature, remember this here, it's temperature, okay, or a way of describing temperature. The amount of energy required for this to happen, we refer to that amount of energy as specific heat. That's it. So specific heat, it's the unit of energy required to do what? To increase the temperature of a unit of mass of a gas by 1 degree Celsius. That's it.